if your definition is abundance,
mathematics? No, it is not. Coincidence.
we're going to talk about something really nice, which is section 5.3, the logarithm. It's the logarithm functions. And something that I think usually seems sort of mysterious to people, but actually is not all that mysterious if you think about it. Okay, so remember let's just recall this thing called inverse function. Called inverse functions. If we have two functions f and f inverse, right? You've got this function f and it's invertible. So it has an inverse function. What that means is that one guy, if you take f of x and follow that with the inverse function, then that brings you back to where you started, right? It returns you the inverse function cancels off the behavior of the original function, right? And it goes the opposite way also, right? If you take the inverse function first, you take f of that, and then those things cancel off each other's behavior. Right, just like, for a simple example, multiplying by 2 and then dividing by 2. Right? Those things would cancel off, those two functions would cancel off each other's behavior. Another way of writing this is to say that f of x being y is the same thing as saying that x is f inverse of y. F of x is y, if and only if f inverse of y is x. Right? Those are the same. That's just another way of saying it. Another way of saying it is to say that if you compose f and its inverse, then you get the identity function, which people write as ID sometimes. The identity function. And the identity function is just a function that doesn't do anything. Right? You give it something and it has it right back to you. So the composition of these guys, again to say that they cancel each other's operation out. And it goes both ways. If you compose them in either way, then you get the identity function. Okay. So this is the inverse function. You all remember it, I hope. So just now, in the last couple classes, we were talking about these exponential functions, right? F of x is b to the x, say, where b is some base bigger than 0, right? And these turned out to be this was a one-to-one function. Right, was an invertible function. This was an invertible function. Right, you remember the graph? If b is bigger than 1, then it was an increasing graph, right? It looked like that. It's an increasing graph, and being increasing, it passes the horizontal line test. And if we had, if b were between 1 and 0, then it was flipped on that sort of graph. So it was strictly decreasing graph. Well, being strictly decreasing also means that you pass the horizontal line test, because you're never going to have a point here and then a point later that is at the same height, right? Because it always the point that's to the right will always be lower. So both of these, in either case, the function was invertible, right? And so we can see that by going like this, by flipping it across, right? If this was b to the x, then this was the inverse, right? This is f of x. If it was b to the x, this guy was f inverse, right? Right? across here. So, something like this. Sorry. Anyway, this again, this is b of the x, then this is going to be the inverse. This is going to be the inverse function. The flip across, the flip across the across the line y equals x. Right? Okay. So this function, right? The inverse function, the inverse of d to the x is called the log. It's called log. Let's say like this. F inverse y is called log base b of y. It's given a name. It's given a name, log base b. So it's called log base b. So, it's this function, the log function. All it does is it cancels off the inverse. It cancels off the exponent, the b. It cancels off the b to the x function. Okay. So, for example, right, if you to write it using the second expression, it's to say that b to the x is y. It's the same thing as saying that log base by is x. Okay. Or using the first one, and I probably should have, I wrote these backwards in my notes, and now I see why I wrote them backwards, so that they would correspond here, what I did here. Maybe I'm going to write it backwards here, so that I'll flip the order here so that it matches up over there. Okay. So the first thing, f inverse of f of x is x, right? So log base b of b of x is x, right? So that corresponds to the first, to the order I have here. Right? Log base b of x is x, right? And the second thing says that f inverse y is y, right? So b of log base b of y is y. Right? I'm just taking the statement here and I'm putting in using b to the x as f and log base b as f inverse. Okay, so I'm just plugging in. Is that confusing to anybody? Okay, so and then the second one, f of x is equal to y, right? B of x is equal to y, if and only if x is equal to log base b of y. Right? So maybe at this point, you just want to get the fact that you have these exponential functions, and then they're one-to-one, and so you have an inverse function, that's the log. Okay. Now, what is this function, the log? This first one sort of gives you the way to think. I think this is the way that people usually think about it. Okay. Right. What does the log mean? Right. What does log base b of y mean? What's the significance of it? Right. Well, right there we see that b log base by is 1. Right. Well, b to the log base b of y is 1. So what is this thing? It is the exponent to which one raises b to get 1. Log base b of 1 is the exponent. Log base b of y is the exponent to which you raise b to get y. Okay, so let me give some, this seems sort of confusing, but let me give some simple examples, and then let's become somewhat clear. Okay, first, if I say like log base 10 of 10, right? So what does this mean? It's the exponent to which you raise 10 to get 10. Well, what exponent do you take on 10 to get 10 back? So 10 to the what is 10?
1.
Yeah, it's 1. Okay, so it's the exponent to which you raise 10 to get 10. Okay, let me give you say log base 10 of 1. Well, what exponent do you raise 10 to get 1? To what exponent does 1 raise 10 to get 1? 10 to the what is 1?
Okay, and power 0.
0, right? Right. 10 to the 0, 10 to the 0 is 1, right? Who hasn't seen log before? Who hasn't seen log before? Sorry. Okay, then I'm going to focus on these. Log base 10 of 110. Well, 10 to the what is 110?
So wait, every time it's something like, right? So it like whatever log it is, it has to be raised to that?
So,
I don't get it.
okay, so just remember, just keep this in mind. What is this thing? What is log base b of y? Log base b of y is the, actually unique exponent to which one raises b to get 1. So like if I say, log base 10 of 1,000, right? Basically, it's to what power do you raise 10 to get 1,000? Well, 10 to the 3 is 1,000, so this is 3. Right, so right, if we're looking at the log base 10 function, right, that says that, well, is 1 is 10, let's say this is 1,000. Right? Okay. So it says that at time 1, log base, for 1, the log base 10 of 1 is 0. Log base 1 of 0. Log base 10 of 10 is 1, right? So once we get to 10, we get to 1. Once we get to 1,000, we get to 2. 100, we get to 2. We get to 2. Right? Once we get to 1,000, we get to 3. Right? Once we get to 10,000, we get to 4. Right? Because 10 to the 4th is 10,000. Right? Okay, so you see, this is a pretty slow growing function. And back here, 1/10. Well, what power do you raise 10 to get 1/10?
Okay, so I have a question.
Yes.
So, do you solve it like, so just say you take 10 to the power x equals to 1/10. I mean, like you're creating.
Yeah.
I mean, that's how I see it in mind.
Yes,
So
exactly.
you're going to say 10 to the power x equals.
Yeah. This thing is really 10 to the minus 1.
Yeah.
Right.
So you would just say x equals to -1.
So this will be -1. Yeah. Yeah.
Okay,
So
so it's just that even an exponents thing where you were trying to make the bases the same and solving for x. I mean, that's how I see it. I don't know. Or is
rather.
that not how it?
It doesn't sound quite right. It doesn't sound quite right. Rather, you think, to what power do I raise b?
I mean, yeah, that's what that's what I thought.
Okay.
But like, in my mind, I solved it like 10 to the power x equals to 1/10. And
Yes.
then, yeah, and then, I use the same logic, like you make the bases the same so you can solve for the power of x.
Right, so you say.
Yeah, and then x equals to 1. Can I do it that way as well? Or can I do it that way?
You can,
that.
that's certainly a legitimate way of
Okay.
thinking about it.
All right.
Okay, so here we're at -1, right? Here we're at -1 at 100, we're at -2, right? At 1,000, we're at -3, et cetera, et cetera. So the function looks like this, right? This is what the log f of x is log x. This is what it looks like. Okay, so okay, what is log base 10 of 2? So what's log base 10 of 2? So I'm going to ask this of everything. Right, here is 2. 2 is here. That should have some value. What's log base 10 of 2? Well, the answer is it's hard to tell. You can't, I mean, there's no, it's not just some whole number. Right? You can't raise 10 to some whole number and get 2. Right? It's some, it's some number between 1 and 2, between 0 and 1, excuse me, closer to 0 than to 1. No, it's not so easy to figure out. In the old days, before calculators, one had these books. I think I told you about these books. The books had square roots in them. They also had log tables. So, okay. So I'm starting to get the idea of what the log is. So these are the simplest examples. Let me give you some more complicated examples. Okay, so this is exercise 9 in the homework. Okay, so this is sort of along the lines of so go to here, number 2. The way you want to think about the second property, so recall that b dx equals y is the same thing as saying that x equals log b of y. Okay, and the way you want to think about this is to say that to each logarithmic statement, corresponds an exponential statement. Okay, and this is what sort of what Stalvia was doing already. Okay, she was translating the logarithmic statement into an exponential statement. Okay, so just to give you an example, if I write something like 3 squared is equal to 9, right, then that's basically the same thing as saying that log base 3 of 9 is 2. Right? Is that clear? That these two are basically the same two statements. 3 squared is 9. Right? 3 raised to the power 2 is 9. This says that 3 raised to the power 2 is 9. Right? The power that you raise 3 to get 9 is 2. Right? Let me write that in English. Right? It says 3 squared is 9. That's the same thing. Right? If we translate these in English, it says that the power to which one raises 3, 2 to get 9 is 2. Maybe to make it better English, I'll say to which one raises 3 to get 9 is 2. Right, too many 2's. Okay. So these, does everyone see that these are really, if I say this, if I say log base 3 of 9 is 2, it's the same thing as saying 3 squared is 9. Right? So if you know, if you understand exponential, then you understand log. So let me ask you to translate a statement. So, okay, so here's a simple one. 7 cubed is 343. What's the equivalent logarithmic statement? Julian, how about you? I don't call on you often.
Log base
Log base
7.
7.
3. 43.
343
Equals 3.
equals 2. 7, the power you raise 7 to, take it 343. Another one, root 2 is 2 to the 1/2. Caroline?
2 to the root 2, sorry, log 2, root 2 equals 1/2.
Yes. Log base 2 of root 2 is 1/2. Right. Okay. Everyone all right? Sorry, is that okay?
Yeah.
Okay, so we're just saying that you know, a logarithmic statement is basically an exponential statement, and vice versa. So so here's another problem. Evaluate the following. Log base 9 of 27. Okay. Log base 9 of 27. Give it a try. You have the answer, Ken?
Not like.
Are you asking a question? Or you
No,
have
I have
you have a question? Okay.
No, not a question.
You don't have a question?
I have
then
like
then what?
a ish.
Okay, Kane, why don't you start off, please?
I got 3 halves.
3 halves? Okay, and how'd you get it?
I broke it down into 3, so I knew it had to be to 1/2 first. And then I brought the 3 to 27 by cubing it.
Okay, okay, so just to slow it down, would you say, well, it's like, look, this is the same thing, if we write this is, that 9 is 3 squared, right? And so what do you need to raise 3 squared to get 27, right? Right, so 3 squared to the what equals 27. Well, if you raise that to the half, you get 3, and then raise that to the cube power, then you get 27. Right, so you this thing to the 3 halves is 27. Right, because you get 3 over 3. Right, you could, just as easily, you could have said, you know, along the same lines, you could have said it like this, right? 3 cubed, 27 is 3 cubed, right? So you're asking 3 cubed to the what? I'm sorry, 3 squared to the what is 3 cubed, right? And it's clear that the what is going to be 3 halves. Easy. Boring. I'm not seeing it before, except for Stalin. I'm just seeing more everybody else. Okay. Another one along the same lines. Log is 4 of 1/32 is 1. Shelby, I'm going to make you do it. If you don't mind.
No, so,
Yes.
okay, I'm not sure. Is it negative 5 by 2?
Negative 5 by 2. Yeah, I think that's right. So let's see. What did you do?
I just did, so I took, I just made it 4 to the power x equals to 1 by 32.
2 to the what?
1 by 32. I just, and then I changed it to the base 2, so it was 2 to the power 2x
Yes.
equals to 2 to the power negative 5.
Exactly.
Yeah.
So you get 2x is equal to 5, and so it's going to be
Negative 5.
negative 5. Right. So you can write it like this if you felt like. Right. What power do you raise 2 squared to get 2 to the negative 5? Well, it's clearly negative 5 over 2. So you can either do it this way, or you can do it this way and read it off, or you can switch, as Starmie did, the logarithmic statement to an exponential statement. Right? So we'll be saying log base 4 of 132 is x. That's the same thing as saying 4 to the x is 1 over 32. Right? So Starmie switched it to the exponential statement and then figured out what that would mean, what that tells you about the exponent. So which is interesting. Okay. Okay. So to give us a more complicated example, right? Let's say that we ask. Should say that. We said that E is this particular base. E is special, so we actually, instead of writing log base B, people usually write ln instead of log base E. So notice ln, and some people read this as lan. String. I don't like it. I don't do it. I read this as natural log. I think scientists tend to call it like, this, scientists. Yes. Scientists and their ilk. Okay. This thing's called natural log, and of course you use it just like you use the other logs, but just has E on the bottom as the base. Okay, so example, e to the 2t minus 5 is equal to 5,000. Okay, and somebody says, what t solves this equation? E to the 2t minus 5 is 5,000. Right? Well, you can translate this. One way of thinking about this is the translation way. Right? What does it say in terms of log? Carol?
Natural log of 5,000 equals 295.
Natural log of 5,000 is 2t minus 5. Right? And then you just solve for t. Right? So what's t? T is going to be natural log of 5,000 plus 5. It's 2t. And you divide everything by 2. And you get that t is going to be this number, whatever it is. Carol?
So we're just going to leave it in that state, that half natural log 5,000 plus 5. So we don't have to solve past that.
Right. At this point, it becomes a calculator problem.
Oh, okay.
Right? You just plug in 5,000 into your calculator and figure out, it will give you some number.
Okay.
Shouldn't it be natural? Shouldn't all, instead of multiplying I was just thinking instead of multiplying it by half, you should put it all over 2, but
It's
it's
the
the
same.
same. Yes, okay.
It's the
Monday
same.
morning.
Okay. Another example. So some population thing grows like 100 times 2 to the t. So times 0, there are 100 people, say. At time 1, there are 200. At time 2, there are 400. At time 3, there are 800, etc., etc. The question is, at what time does p to t equal 1,000?
So you just do one.
You just say, you set 1,000 equal to p to t. Right? You want p of t to be 1,000. And the question is, to solve for t, how do you get the t? What t works? You know that it's going to be between 3 and 4 somewhere. How do you get the t? Does you had this before? Maybe you can tell me this, Kelly.
I have a question. If you first divide by 100 to isolate the 2t.
Yeah.
Okay, so then you do 1,000 divided by 100 equals 2t.
Mhm.
So then 10 is my division.
So 2t equals 10. Right?
So
Exactly.
A plus C equals B. So
So let's
log
translate.
2 of 10 equals t.
So we get it down into this exponential form, right? And then we translate to the logarithmic statement. And so t turns out to be log base 2 of 10. Whatever that number is.
And again, we just leave it in log 210
Yes.
as the answer.
Yes,
Okay.
that's fine.
So if you look at a problem, how do you know whether you should be using log or natural log?
Well, here in this one, you've got 2 to the t, right? So it's sort of a natural, it sort of makes sense that you take this statement and then you translate it into a statement about powers of 2.
Yeah.
So
Are there certain graphs, like when you look at a graph and then you have to translate it over, that I remember doing this and I remember looking at graphs and having to figure out if it's a natural log or log.
really, actually, the two natural log or log-based something else are actually related to each other. They're actually just multiples of each other. So, if you can do it in one, you can always switch it to the other. We'll get to that. We'll get to that in the next section. Okay. So let's go on. I think maybe we're going a bit too slow. You don't seem. I know you've seen it before, but even given that, you seem maybe not great. So let's go on to the next section. Properties of logarithms. So here are the two main properties. So log has some really nice properties that other functions, that most of the functions, basically no other functions have. Okay, and here they are. Property 1, log of xy is, maybe some of you know this already, log of product translated Think about it.
Is it x plus y? I'm guessing.
You're guessing. You're not far off. It's log of x plus log of y. So the log of the product turns into the sum of the logs. Right? Log of product is the sum of logs of factors. Number 2, log base b of x to y turns into, maybe this you guys remember, log of something to a power, well,
Y log, x.
turns into multiplication. So you can pull the power out into makes it a multiple. Is there no mnemonic that people have developed? There was no song or anything.
If you look, you've never heard the quadratic equation song.
You see, it must be a new development. Okay, so, well, in any case, the log of the product turns into the sum of the logs, log is something to a power, you can pull the power to the outside. So the text also lists other properties, but they're all sort of not as important as these. So for example, here's one of them, log base b of p over q. And it says, well, this is log base b of p minus log base log base b of q. That the log of a ratio turns into the difference of the logs. Okay. But this is actually the same thing as this one, right? It's the same as the first one because we could just write this ratio as log base b of p times q to the minus 1. Right? P over q is the same thing as p times q to the minus 1. Right? And so using the first property, we'd see that this is log base b of p plus log base b of q to the minus 1. Right? What's log base b of q to the minus 1? You can pull the minus 1 out by the second property. Right? Which is log base b of p minus log base b of q. Right? So this one you don't have to remember. If you know the first two properties, then that one is just, that's already included, right? So you don't need to know. You don't need to know. They also give these other properties. For example, log base b dx is x. But that's the same thing as this property, right? Right? Because what does the second property say? It says we can pull the x out. This is the same thing as this. And it follows from this, right? Because what can we do to the x? Well, we can pull it out. Okay. Right? So this log base b to the x is x log base b b. What's log base b of b? What power do you raise b to get b? 1, right? So this is x. Right? So again, there's these properties, but you don't really need them. Right? Or you can just remember that log and b to the x are inverse functions. Right? So log base b of b to the x is x by definition. So these other properties, that's not really the point. These two properties are the properties of the log. These are the properties that actually characterize the log. Nobody else does this. So, okay. So you can use these properties to. So this is sort of a weird thing to do, but you can do it. You can use combine terms, or expand terms, depending on how you feel. So, let me give an example. Somebody gives you 1/2 log base b x minus log base b plus x squared. Well, just for the heck of it, we're going to combine everything into one term. Let's rewrite this guy. We've got 1/2 times log base b log of x. Well, we can put the 1/2 back in. Right? So this is log base b x to the 1/2. Right? Again, here, if we feel like it, we don't have to think of it this way. We could put the minus sign back in. Okay, so this is plus log base b. You don't have to do this one, but you could. Okay. And so now we've got the sum of two logs. The sum of logs turns into the log of the product. So this is the same thing as the log of the product. Log of the product. So first we use property 2, and then we use property 1. Okay. Property 2 says we can pull the exponent out or put it back in. Okay. Property 1 says we can turn a sum into a product, or log of a product into a sum. Is this okay? Yeah. Okay. Another example. Let's say log base 10 of, say, x squared minus 16 minus 3 log base 10 of x plus 4 plus 2 log base 10 of x. Maybe see if you can do it. Should take about a minute to see if you can do it. Sorry, I'm going to make you do it.
Okay. Can I just do the final answer first, and then or do you want me to work through?
Work through
Okay.
this, 'cause
So I used the multiplication thing.
mhm.
So I did x squared minus 16 times x plus 4 to the power negative 3 times x squared. Is that right?
Yes, except you forgot one thing.
Oh, log.
Log. Yeah, and that's it.
Yeah. I mean, and then I just multiplied.
No, that's it.
Oh, I
You just
don't,
leave it.
okay.
That's it. So, I mean, if you wanted to slow it down a little and do it in pieces, right, you could say, but that's the right answer, too. You could say, well, the first thing you do is to move this minus 3 in. Right? Move this minus 3 in, and move the 2 in also. Right? And then you've got sum of logs. Sum of logs turns into a product. So you get x squared 16, x squared, x plus 4, which is 3 on the bottom. Okay. Good. Easy, right?